So if any of you feel the need to get up and stretch, you won't offend me. It's been a nice day. Okay, well, I'd like to continue talking about the materials properties of graphene, and then we'll segue to talking about mechanics of graphene particularly. So the thermal transport in graphene is of great interest, and Alex Balandin at UC Riverside was the first team to map the thermal conductivity. They used a different geometry than this, and they used the material obtained by micromechanical exfoliation from graphene. So we were interested in our CVD chrome graphene and whether its thermal conductivity might differ significantly for some reason from the Scotch tape exfoliated graphene. And we're using a so-called Pugno geometry. So if we have a circular membrane, and so we have these holes in a silicon nitride membrane in a square array, and they have a diameter of about 2.7 microns in this particular experiment that we did. So we are transferring our CVD graphene onto an array of holes to try to create membranes. And if the membrane is circular, it turns out there's an analytic solution for extracting thermal conductivity if one can measure the thermal contact resistance and assuming a thickness of 0.335 nanometers, the interlayer separation in graphite, then the other geometric parameters are known so that the thermal conductivity in principle can be extracted from that sort of measurement. What we're doing here is we're using a Raman system, and we separately, as I'll show you in a moment, map the shift of the G-band, or in a new experiment, the 2D band peak. So a shift of peak frequency as a function of temperature in an environmental cell. And once we've calibrated that becomes useful when we irradiate with the Raman laser. So we have a power meter where we measure the power with the graphene present. And we've actually deposited a 500 nanometer thick layer of gold on top of the silicon nitride for better thermal contact. And we're fortunate that our transfer is not perfect. And that allows us, for example, to make measurements of power when there's no graphene membrane present, because typically, not too far away, there's a membrane that's broken. And so we simply slide the sample over, measure the laser power with the absence of the graphene membrane, slide it back and measure the power with the laser power meter in place when there is a graphene membrane present. I can tell you that the largest error in the measurement is the measurement of the laser power, and that introduces the largest error in capital thermal conductivity. So in this environmental cell, what we're doing is, in a home belt cell, we're measuring the shift, for example, in the G-band peak as it moves at low temperature near 1580, where it would be at room temperature, for example, to redshift values at higher temperature. So the temperature coefficient of the G-band peak allows us to extract that thermal contact resistance. So these points represent when the G-band is shifting on the graphene that's on the gold on the periphery of the membrane at And this is the shift at the center point where we're intersecting the center of the membrane. One thing that's important, it turns out, is a very good measurement of the laser beam size where it intersects the graphene. So we improved on what Alex's group had published by a simple technique of using the edge of a broken wafer. And another thing we've done, just to give you the whole story, because we published 3 papers on this topic, is we try to detect the influence of ballistic phonons, or long wavelength phonons, that are expected to play a role in thermal conductivity of graphene by measuring different size membranes, including up to 10 microns in size. So this is now a separate experiment. And we've also shown that using the 2D beam, which is at a larger wave number value, gives a more accurate value for the peak shift, and that's more useful than using the G beta as sort of a fine point. So the main difference, as I show you the data set later, between high-end values for thermal conductivity and low-end values of thermal conductivity, and our values are somewhere between, is the measure of the optical absorption of the membrane. And so I think that that's something that will be improved in the future. And we're not saying we're right and the other people are wrong, we're just saying we're getting different values. It might be that for Bolandin's group, there was some impurity present on their membranes that was also absorbing as a problem.
Are you using the same formula for the resistance?
For the thermal, for the contact resistance.
For the other, and the one logarithmic one. You get that? You're using the same formula they use?
They have a different configuration in their first experiment. Bolandin now is starting to use this for so his formula would be different.
And the thickness of the graphene is the diameter of the camera?
Yeah, everyone assumes 3.4 nanometers, 3.35. It's debatable, yeah, that's right. Yeah.
So
I think to have a common way yeah, it's the way of having a common way we need to discuss it. Because graphite, one of these that makes sense. And so these, just to go straight to the point of what the values are, we have a temperature dependence, as you see, that seems to follow that of graphite. So we have some 3 sets of data from the literature for graphite. And you'll notice it's interesting that we have high-end numbers occurring at lower temperatures, around 100 Kelvin. And so the Diamond Bowers collaboration is shown here, where they measured the higher temperature on about a 40 micron lateral dimension diameter Corbino geometry. And you can see that the error bars are fairly large with this technique. So one way of making error bars smaller is either to make better measurements of that laser power with more uniform samples, or to switch to microcalorimetry as a separate technique. And as we get better and better CVD-grown graphene over larger and larger areas, it makes it simpler for the people who do microcalorimetry, including our collaborator here, Nishi, to configure those sorts of experiments. Now, one thing I'd like to mention, which I think is quite interesting, is that we're used to talking about extremely high thermal conductivities for diamond and graphene and graphite and plane, around 3,000. But isotopically pure diamond, that is to say 99.9% C12 diamond, around 140 Kelvin, has a thermal conductivity of 41,000. And it's predicted that if one were to try to make measurements with single crystal diamonds at the maximum of the curve predicted for diamond theory, it might not be possible to do experimentally because the value might be 200,000. So another fascinating thing that we hope to soon probe with graphene is we have acquired 99.999% pure C12 methane. We're hoping to make thin graphite and also graphene over a large area, large enough so that the thermal resistance of that piece will be large enough to allow it to be measured at its maximum, because we expect to have a similar sort of response as diamond, probably shifted in temperature. So it would be quite fascinating to have an analog, not a perfect analog, but a superconductor, moving charge without any resistance supported on a structure versus suspended as a membrane, the values measured are much lower, about 600 watt per meter kelvin. And it seems not to matter all that much about what the substrate is, also from recent work from Blandings group on other substrates than SiO2 and silicon. So there are out-of-plane, long amplitude phonon modes that are contributing strongly to these high numbers that are suppressed by being in contact with the substrate. So the thermal conductivity of graphene when it's in contact with the silicon wafer at room temperature is about a factor of 5 lower. It's about 600 watt per meter kelvin. So as the experiments progress, more and more will be learned about which sets of phonons are playing a critical role in contributing. But clearly these long wavelength phonons probably play a very strong role. Also, we're the first group to make the measurements in relatively good vacuum. And not surprisingly, the thermal conductivity values reported are influenced by having been measured in air and atmospheric pressure. So there are collisions with gas phase molecules that are removing heat that might make the thermal conductivity appear to be higher than what it is. So ultimately, we need to make good measurements in vacuum too, so we can report intrinsic values or be able to correct for the influence of molecular collisions removing heat. In terms of this work with C13 label material, I had mentioned to you this morning that we can make graphite by depositing a nickel and allowing it to precipitate as we cool down. Using a nickel foil, we can end up with 300 nanometer thick, 1 micron thick graphite. And another thing we've done is to use C13 labeled synthetic graphite to be able to make C13 labeled graphite oxide to better understand its structure through solid state NMR. And so I'll quickly tell this story. It's not so closely related to mechanics, but two-dimensional NMR is a very powerful method of learning about the connectivity of bonding networks. And if we were to try to acquire this spectrum, which took 14 hours by our colleague at the University of Illinois Chicago, Yoshi Takeshi, who's an expert on solid-state NMR, with normal abundance material, it would have taken 100 million times longer, so it never would work. So we have to increase the C13 concentration because that's the magnetically active nucleon. C12 is NMR silent. And this two-dimensional NMR, if you collapse into a one-dimensional spectrum, you have peaks that are overlapped. So by doing it in multi-dimensions, you can spread the information content out and learn more about the chemical connectivity of the bonding networks. And so this paper was published in Science. And I think it will also be of use in understanding mechanics and composites and so on. Because if we don't, in some sense, with certain systems, have a very clear understanding of the binding or bonding between graphene or chemically modified graphene and the matrix, then we're at a loss of information. We're sort of guessing why the mechanics works out the way it does. And it's these sort of C13 labeled graphenes that will allow solid-state NMR to be very useful in composites, also in understanding how the chemically modified graphene is bonded to the polymer matrix. So what is graphite oxide? It is also a layered material, and the chemistry of the individual layers is like this. So these chemical handles, like epoxide groups, hydroxyl groups, I'm not showing, but carbonyl and carboxylic groups on the edges, mean that this material really is quite different than pristine graphite. So we start with graphite, and then we do chemistry where we wedge intercalants between it, and we hit with a very strong oxide like potassium permanganate, or potassium perchlorate, and that drives oxidation of the layers. We end up with a layered material that's actually swelled. So at 0% relative humidity, it has an interlayer separation of about 6 angstroms, and at 100% relative humidity, it goes up to about 13 angstroms, and you can just cycle back and forth. So it breathes, and the reason why it's swelling and contracting is because the amount of interlamellar water between the layers is influenced by the humidity. So this is so hydrophilic after reaction that water will go between the layers and make this interlamellar compound where the layers are still stacked. Also, the chemistry is still being worked out, but it's not periodic. It's aperiodic, which is why we use solid-state NMR, or otherwise we could use crystallography. But the reactions in the plane don't typically happen so that one would have a periodic ordering of the chemical functional groups. So in terms of mechanics, you can think of these as handles for bonding to matrix materials. And also, of course, the mechanics of this will be different than graphene itself. This has an extinction coefficient essentially equal to 0 and invisible, so it's optically transparent. We've so disrupted the delocalized pi electrons that it's no longer strongly absorbed in the visible. And you'll see that when I come to talking about this layered material as a paper-like material. It's quite thick, you can still see through it. It's also electrically isolating, except for perhaps ionic transport. So for electrons and holes, they don't move in this material. The only way we can convert this back to being electrically conductive is to hit it with any of a large number of reductants. And one example is hydrazine, so they will knock out some of the oxygen functionality and return it not back to pristine graphene.
What's the concentration of oxygen rest of those into
Yeah.
carbon roughly?
Yeah, the typical stoichiometry is about C2O1 H about 0.6. So it's very high oxygen.
Is that a pretty accurate figure, or is it?
That's a great question. It's not a stoichiometric compound. It's not a stoichiometric compound.
No, but I mean, it's that.
No, this is pretty typical, but these numbers move depending on who does the synthesis and exactly what
So
methods.
within what range percentage was 10% or?
10 to 15%. Yeah. Depends on the starting graphite, on which oxygen is used, on the scale of the synthesis, and things like that. So there actually in this material, the stoichiometry might be C10 O1 with a relatively small amount of hydrogen present. And so we can reduce the material in different solvents and have something akin to graphene, relatively strongly osmotically absorbing, pretty electrically conductive, floating around as a platelet to play around with. So one thing we did was there's a lot of chemistry that I think is perhaps of less interest to this audience, maybe with the exception of Larry. So briefly, we did a parametric study with different isocyanates. Phenyl isocyanate was a good way of functionalizing those graphene oxide sheets. And once functionalized with phenyl isocyanate, we could move out of water solvent into dimethylformamide, which is a compatible solvent for many polymers, like polystyrene. That allowed us to then mix the material in polystyrene, and we could also, in dimethylformamide, react with 1,1-dimethylhydrazine. Hydrazine is mixed with a little bit of water. You don't want to introduce water into the polystyrene mix. And so by using 1,1-dimethylhydrazine, we have a reductant that could be in the EMF of water. And then we mixed the material and allowed it to fall out of the solution by using an anti-solvent, ethanol. And so we end up with material at the bottom, which is a composite. We could hot press that material and then cut it and take these scanning electron microscope images. And I apologize, the scale bar on this one should be about 1 micron. I need to add scale bars. So I think for the mechanicians here, this is now a fascinating issue. And I'll tell you some of the fascinating parts from my point of view. You'll notice these are not flat. They're highly wrinkled and crumpled. Okay, so in a moment, I'm going to show you electrical percolation data that shows that this polymer matrix composite with polystyrene, which is of course electrically insulated, becomes electrically conductive at 0.1 volume percent loading with these platelets. Okay, now geometric percolation for pancake-shaped ellipsoids, for the oblate ellipsoids in terms of concrete mechanics and so on, this has been, of course, well studied, occurs also at 0.1 volume percent loading for an aspect ratio of 1,000. Okay, so pancake, oblate ellipsoid, 1,000 diameter, 1 unit thick. However, actually many of the platelets satisfy that criterion if they were flat, but because they're crumpled and wrinkled like this, the effective ellipsoid that they are fitting inside of has an aspect ratio mesoscopic physics of whether it's tunneling through a thin polymer layer or in direct contact still hasn't been worked out in terms of temperature-dependent studies. So I think a very exciting area which I don't see anything in the literature on. Of course, membranes and wrinkled membranes and so on have been studied, but not issues like when would percolation occur for a structure like this, and what's happening in terms of mechanics, in terms of these ridges and so on. One might think that this is disadvantageous if you want to have a load-bearing composite, having wrinkled structures that can breathe too much instead of being immediately taut is perhaps a disadvantage, but it might be an advantage in a rubber-like or elastomer system. You're probably aware that percolation limit for spheres is around 40%. So if you put carbon black into a rubber material, small spherical particles about 10 nanometers in diameter, you can rigidify the rubber. You can push its stiffness up significantly, but you embrittle it also, because you have to add so much material to get it to be stiffer. And perhaps also you want to imbue it with electrical conductivity at the same time. So these sorts of wrinkled sheets, if you embed it in elastomer, they may remain as a percolating network electrically, and perhaps thermal as well, and imbue that rubber with good thermal conductivity. But they can breathe in a sense and relax back in terms of their structure. I can tell you there was a very exciting report given by Alex Bolandin in terms of directly exfoliating graphite. So there has been progress made. I told you this morning that you couldn't as easily get graphite itself to fall apart into individual layers as we can graphite oxide. Graphite oxide very easily falls apart into individual layers of water and aqueous suspensions. But progress has been made, such as by Johnny Coleman's group at Trinity College in Dublin. So one can work hard and get some exfoliated graphene and multi-layer graphene from graphite itself. And Alex Bolandin reported at a weight percent loading of 5%, they had pushed the thermal conductivity of an epoxy composite to 7 watt per meter Kelvin, which is quite amazing. Some of you might know that conductive polymers are really a misnomer because they have about 80 weight percent of chopped high conductivity carbon fiber in them that's been compatible. So they're actually mostly carbon fiber, but they call them conductive polymers. And they might have thermal conductivities of 5%. So it's believed the reason for the difference, we had thought about this in my group, is, if you look at other choices like crossed fibers, you sort of touch at a point, not really, of course, it's an area. But same thing with nanotubes. Nanotubes have not really imbued polymer matrix composites with good thermal conductivity from an engineering point of view. There's been a lot of good physics done. And again, they're crossing at a very small contact area. But graphene can overlap graphene and probably have more effective phonon transfer in one sheet than another. And so we looked at percolation in terms of standard treatment with this critical exponent and measured the electrical conductivity and modeled the finite element analysis based on the thickness of our hot press films. And we got a value of 0.1 volume percent for percolation. So that rivals composites with high aspect ratio. Then, inspired in part by Bucky Tube paper, and also a paper that had been published in 1973 by the Imperial Chemistry Laboratory, where they had used vermiculite and exfoliated it in water and made a thin film paper-like material in mechanics. We filtered these graphene oxide platelets and onto a simple alumina filter, and they actually layered up very nicely. The filter clogs almost immediately and then just drips slowly. So the details of the assembly we don't yet understand. And so this layered material, actually in scanning electron microscopy, looks a little bit like baklava. And I had a wonderful experience because I talked about this shortly after it was published in Alexandroupolis, Greece, and then went across the border to Istanbul with my family on the train. Gave the same talk in Istanbul, and I mentioned in both places baklava. And apparently there was a just for fun type of argument that was settled in a European court. Who invented baklava? blah, blah, blah. And apparently it was the Turks, so they won the court case. I think it was purely a kind of a humorous thing. So that was explained to me in terms of these images. So what I want to emphasize to you is something quite similar, quite simple, but I think it's important to make sure we understand it. Let's think of this stack of business cards as a single grain of graphite oxide. Okay? I told you about the interlayer spacing, and you can imagine there are water molecules between the layers. My idea here was to throw up all the individual sheets and have them come down in such a way that we get aerial overlap like that. Okay? And that means we can make any area we want. Obviously, it just depends on the amount of material and what clever processing we think of. So this material has become very interesting recently for the story that I'll tell you, in which case these were stacked but were reduced graphene oxide platelets. And I'll tell you that story in a second. It's a result from the Naval Research Lab that I think we'll be hearing about soon. They reported it at a conference that I was at. But let's continue the discussion in terms of this graphene oxide. So I told you, small extinction value. That's a micron thick, and you're reading through it. So quite different. If this were reduced graphene oxide sheets, this would be shiny like graphite. So you can also make the large area of material from a conductor. So we focused on the mechanics of this material, and we measured strengths as high as strength of aluminum, around 130 megapascal. And the modulus values were of order 20 to 40 GPa. Now, I don't delve into great detail here about the mechanics of this paper, other than to note that collaborator Vivek Shenoy and his team have, I think, well explained the mechanics of this in terms of the hydrogen bonding that is present between the sheets and interlamellar water. So the strength and stiffness is pretty well rationalized in terms of molecular mechanics and dynamics modeling done by Vivek Shenoy's group at Brown University in terms of the interlamellar water and load transfer being modulated through the hydrogen bonding network. I also want to leave you with the picture that I think this material will be very interesting if you can stitch the layers together covalently instead of only through hydrogen bonding. And then you might also affect chemical changes in other ways that I'll tell you about in a moment, like the Naval Research Lab. So we built a little jig that operated inside of a scanning electron microscope and used simple plate mechanics to extract rough values for Young's modules. And then I'm not telling you all the details of the mechanics, but we did measurements with dynamical mechanical analysis of simple strips and studied also the function of the mechanics as a function of water content in the columns. Now, the result from the Naval Research Lab was quite surprising, and one of their physicists was at a conference recently in Cambridge, Massachusetts. And, he started his talk by saying, I'm a physicist, I hate chemistry, but because I work on sensors and lead the sensor division, I have to know a little bit of chemistry. What they have done with these overlap and stacked platelets is make membranes where they get Q values as high as 10,000. So the quality factors that they get for mechanical resonance of these membranes made from overlap and stacked reduced graphene oxide platelets is much higher than the graphene itself. So when I come to my other talk, we'll see Q values only around 100 for resonating graphene. So that's interesting. But then what they did is they fluorinated it. And so they drove fluorine reactions. Graphite, if you fluorinate it, you get a intercalation compound where you have fluorines weakly bonded to the carbons. But it turns out the pre-stress in their drum-like membrane is of the order of about 1 GPa. It's a high pre-stress. And they then heated their membranes, which are made of these stacked and overlap, reduced graphene oxide, functionalized with fluorine. And as a certain function of heating, the thickness suddenly dropped by about a factor of 2, and the modulus went up from about 150 GPa to 800. So what happened? But if I tell you that the density of stacked and overlap reduced graphene oxide paper is about 1.7, what do you think happened? And the modulus jumped up to 800. density is just about double to 3.4. Density of diamond is 3.5. The modulus is approached that of diamond. So I find this extremely exciting. And when Eric Snow said that, I sort of raised my hand and he said, well, I think you've made diamond. And I said, oh, okay. I'm sure he went back and told his colleagues. And so they were ready in the manuscript. But it's not inconceivable that we will soon see, meter-wide strips of this sort of stacked and overlap plate that we just have to fluorinate and heat it. The problem is, how do you generate this sort of compressive stress that might be critical? So first we have to find out, is the 1 GPa of tension, which is also pretty good under compression, critically important to driving the sheets together once the fluorine atoms leave. When the fluorine atoms leave, you essentially have carbons on different layers that are free radical sites. Okay, and if they're lined up, they can form a covalent bond and zipper the material together to make something like diamond. So this, I think, is extremely interesting also because there may be ways of getting intermediate structures like electrically conductive diamond with some sp2 bonding and some sp3 bonding. Now I'd like to switch to a different topic where these reduced graphene oxide sheets have been very useful. I'll tell you about briefly some work we've done with supercapacitors. And we were the first to publish in Nano Letters, and since then there have been thousands of papers about the possibility for graphene and supercapacitors and batteries. And one of the exciting challenges is if we could push up the energy density in electrochemical double layer capacitors to close to that of a lead acid battery, but get the cycle life of a supercap. So cycle lives of supercapacitors, ultracapacitors, it's the same thing, terms are synonymous, are of the order of millions of cycles. So a lead acid battery that we have in our car gets about maybe 2,000 cycles and then we have to go and have it replaced. So if we could get the same energy density but never have to replace it, that would be a very exciting advance. So the type of capacitor we're used to thinking about from high school physics is a dielectric wedge between two metal films. And we polarize the dielectric. This is a different situation. We have an electrolyte in contact with some high surface area electrode. And this is referred to as the collector, the aluminum foil, for example. And when we attempt to polarize, let's say, this high surface area carbon positively, for example, in the half cell on your left, what will happen is the anions, the negatively charged ions in the electrolyte will decorate that surface. And that's called the double layer. And so a very small separation between charges, the order of about a nanometer, and the very high surface area add up to a very large capacitance. So the question is, with graphene's very high specific surface area and its good electrical conductivity, can we get a wonderful increase in surface area and very good contact with electrodes? So this is called an electrochemical double layer capacitor. Notice that the energy density is proportional to the voltage squared. So maybe graphene compared to the current carbons that are used will also allow using new electrolytes like ionic liquids that operate at much larger electrochemical windows, larger voltages. And so those larger voltages could also allow higher energy densities as long as the system is stable. So this was the paper we published, and this first paper we did only as well as existing systems based on activated carbons that have similar values for aqueous and organic electrolytes. Water has an electrochemical window of about 1 volt. The organic electrolytes were developed to expand the voltage window up to about 2.7 and 2.8. And ionic liquids might have voltage windows of 3.5 to 4. And that led to a startup company located in Austin, Texas, to try to expand this. So briefly, at different length scales, we see that the overlap and stacked reduced graphene oxide material, when it's dried down, is still wrinkled and crumpled. And then in scanning electron microscopy, it has this sort of pebble-like structure. And this is what the particle surface looks like. So the idea here is to infuse this carbon with an electrolyte and see how it performs as an electrolyte. It did pretty well to start out. Briefly, we assemble what are called 2-cell systems, and we use organic electrolytes like tetraethylammonium, tetrachloroborate, cocaine carbonate, or acetyl nitrile, and so on. And we make measurements of cyclical ammograms and also constant current charge, discharge curves to extract the specific capacitance and also energy density. And so this is simply showing that this material rivals activated carbon. It has good time response, and it shows good values of specific capacitance. Its energy density is no better than what's in the marketplace now. An interesting thing about these sorts of materials is typical failure of activated carbon. Now, some of you may know what activated carbon is. So we take wood or charcoal or coconut shells or bits of different sorts of seeds like peaches, and we activate them with certain sort of activants like potassium hydroxide. And that drills holes chemically that are nanoscale, pores throughout the structure. And you can enormously increase the surface area, and then we put it on our home to filter our water. It doesn't have to be electrically conductive. Or we pyrolyze it here a bit so it becomes electrically conductive. So the main reason why commercial capacitors fail is because there's always a little bit of water left in them. If you'd prefer there was no water at all, you're operating it at 2.7 volts with an organic electrolyte. There's a little bit of water that every time you pass 1 volt, if it's in a region where it can be hydrolyzed or electrolyzed, it produces hydrogen. And hydrogen builds up in the cell, and after many hundreds of thousands of cycles, the pressure gets so large that it bursts. So they build a pressure release valve in so that it doesn't spill all over the neighboring cells. And that one's out of the picture. Now, there is a chance that graphene will allow getting rid of all the water because it's a completely different structure. The reason why you can't get rid of all the water is because of trade-offs. If you try really hard to get rid of all the water, you reduce the surface area too dramatically by your processing. And so you have to currently accept, due to capillary condensation, in these tiny pores that there will be some water in the activated carbon. We just published this paper in Science. It might be of interest to you, and it should be of interest to Harry. I'll jump ahead to negative curvature carbon here. We think we might have made a negative curvature carbon for the first time at large scale, but the electron microscopy is quite challenging. So what we did was we took this sort of material. So if we take graphite oxide, dry it down, and then we irradiate it with the microwave. You can also do this by thermal shocking. You can transfer it through a very hot furnace and very rapidly heat it. It kind of popcorns and expands enormously volumetric. And it has this sort of accordion-like structure. And one of my postdocs, Yan Wu, decided just to activate this in the same way that people activate the other materials I told you, like wood. And we ended up with a very strange result. We didn't expect this at all. After the KOH activation and washing out potassium carbonate, which is one of the products, so you adjust the amount of potassium hydroxide, do a parametric study, and at a certain ratio of potassium hydroxide to the microwave expanded graphite oxide, we get BET surface areas by nitrogen adsorption measurements of 3,100. So larger than the 2,600 number that I told you before for graphite. So it turns out that the electron microscopy done by Eric Stock at Brookhaven National Lab shows that this entire material, everywhere he looks, consists of one atom thick walls, but now distributed in three-dimensional space. And electron energy lost spectroscopy in XPS by colleagues shows that it's all sp2 bonded carbon. There's no sp3 bonded carbon in it. There's very little hydrogen and essentially no oxygen. It seems to be pure carbon. So somehow the KOH is playing a kind of a remarkable role in restructuring the carbon to have these atom-thick walls present with very, very high porosity with a distribution of what are called micropores, which means nanometer scale, and mesopores, which means few nanometer scale, distributed throughout the carbon. And this has extremely high values of gravimetric capacitance and energy density approaching lead acid battery. So we think it's a very important breakthrough, but it's also very interesting in terms of the potential structure of the carbon. The high surface area can actually be rationalized because if you introduce hexagons, sort of inflating the surface. And so these numbers of 3100 are reasonable in terms of some simple modeling that can be done. I wanted to say something when Harry, for example, mentioned that C60 has been very useful in the solar cell. So I want to briefly make mention about the importance of graphene in the future. And it's a very simple argument. The work function of graphite is about 4.8 electron volts to 5, depending on the graphite combinations. Graphene has been measured to be about 4.6 electron volts. So in C60, the electron affinity, I believe, is 2.6 electron volts, and the ionization potential is 7.4. If you add those numbers together and divide by 2, you get the work function of graphite. If you take a larger fullerene like carbon-96, its electron affinity will be larger, and its ionization potential will be lower. The sum, again, will be very close to 10. Divide by 2, you get the value for graphite. As you inflate the fullerene bigger and bigger and bigger, and you make it finally extremely enormous, so that its radius of curvature is so small that locally it looks like graphene, then the electron affinity and the ionization potential will essentially be equal. And so we have a situation here where C60 is a wonderful electron sponge. And when you have a solar cell, a photon comes in and you create an electron hole pair. If they recombine, you lose the energy. You need to get the electron and the hole to go out in their respective circuits and collect the electricity. So C60 is very valuable because it's an electron sponge, but it doesn't like holes. It doesn't like the positive charge. It has large electron affinity, but the ionization potential is not appropriate for grabbing the hole. Graphene, on the other hand, has an even much larger electron affinity, so it's going to be even a better electron sponge, but it's also a wonderful sponge for holes, so it can play a role in both parts of the solar cell in a sense. So with this, I'll stop this portion of the talk, and then we'll segue to graphene mechanics. Are there any questions about any of the materials aspects or the sorts of materials that we've made? Okay. Caveat is I am not a mechanician. I'm more a physical chemist and material scientist. So I'll do my best on the mechanics and feel free to correct me and call in other things if I make an error. So we've already talked about these sorts of things in terms of properties of graphene. Let's take a look at how we can extract modulus and prestress, and we'll talk about fracture strength, a little bit about friction of graphene versus thicker layers. For example, graphite, the adhesion of graphene to underlying substrates. So all of these topics are of interest, and ripples in suspended graphene, how they can be created by varying temperature. We've already talked about wrinkles. I think it's a fascinating new test system in a sense if we can figure out clever ways of knocking out controllably a certain number of atoms to test whether continuum mechanics will work or fail, whether corrections will be needed. And then influence of the sorts of defects that might be present in graphene, multilayer graphene, and so on, a little bit about some of the dynamics. And I told you that the dynamics of these overlapping stack platelets was surprising in terms of NZ1Q. So there has been work, very nice work from Columbia University. We were asked earlier, could nano-indentation be useful? They actually used indentation, but with an AFM diamond tip of 2 different radii of curvature. And in these experiments, what they're doing is they're micromechanically exfoliating using the Scotch tape method onto an array of alternating 1.5 micron and 1 micron holes. So this is the effort from Lee, first author, of Professor Jim Holm and Professor Jeff Kaiser in their respective groups at Columbia University collaborating. And they wanted to measure the mechanical properties, including fracture strength. And so what you're looking at here graphene that's come off. Of course, there are many other areas that weren't successful, that were too thick and so on. So they zoomed in optically on the one that's promising, and then they have opportunity to measure over different diameter membranes and to use these diamond tip. They actually found they had to use the diamond tip, not silicon carbide, not silicon nitride, because the graphene was actually strong enough in their samples that those others might be deforming too much. So this equation here,
How big is the tip with respect to the
I believe one radius of curvature was 15 or 17, maybe, and the other was 25. And there is a strong stress concentration that was treated and modeled by finite element models. So they're explaining that in this equation, they're using sort of a two-dimensional equivalent for Young's modulus, so the units of that and the pre-stress in terms of newtons per meter rather than gigapascal. If we divide by 3.35 angstrom thickness, we can convert back to the units that we're more used to for three-dimensional materials. So this is showing that F is the applied force because there is a significant pre-stress that I'll show you momentarily in the film. Again, it's like a drum scheme. That just happens because of the deposition. There's something about rubbing down on these membranes. They actually see that the graphene is recessed a few nanometers and stuck to the wall of the membrane. And they can clearly show that there is a pre-stress present from the data. Okay, so this Q, as shown here, is derived from Poisson's ratio. And delta is the deformation, A is the diameter of the membrane. So they're using a third order of nonlinear elasticity and fitting the parameters as a function of load versus indentation depth. And I believe from one flake they got 7 and 6 of the 1.5 and 1 micron membranes. And from flake number 2, they got 5 and 5. And they made multiple measurements on each membrane, so they ended up with 63 data sets to reduce. And some are with the smaller radius of curvature with diamond tip, and some are with larger radius of curvature. So this is explaining why they use this nonlinear elastic behavior as shown here. So this may have more meaning to some of you than it does to me, so I'll leave it here to read. I'll be posting my talk on the CISM website, so you'll have access to the PowerPoint slides as well. So they say at the end here that numerical simulations of graphene sheets and nanotubes suggest that a nonlinear elastic response is appropriate. So they're using this second order coefficient E and third order coefficient capital D. And this shows the values of this each mean parameter, which had a mean value around 345, just at a Young's modulus that we would have expected for the graphene. You can see the pre-stress values are pretty high. Some as high as 1 GPa. The authors point out that pre-stress in the film exceeds the strength of many typical materials. And they, of course, got different values for the force at break for the smaller tip versus the larger tip. But when treated with finite element analysis in terms of the two different radii of curvature, those collapsed on each other very nicely. So it was a self-consistent picture that they developed. Here, the radii of curvature, 60.5. So actually, in essentially all or most of the membranes, they had failure occurring at the ultimate strength. And this is again because, well, one can guess that when they do this micromechanical exfoliation, probably the graphene that's transferred is grain boundary free. Okay, that's an interesting question, but I think that's probably the case. Or at least the grain boundaries were not significantly influencing strength if otherwise. But I think that that's a reasonable conjecture, although still to be proven because of the nature of the exfoliation and the way it works. Okay, switching to a different topic. The same group collaborated with Rob Carpet with his team at University of Pennsylvania